Good evening, everyone. I'm Manesh Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to the live weekly interaction for the NPTEL course Engineering Mathematics 2. This course is taught by Professor Jitendra Kumar from IIT Kharagpur, and the NPTEL course code is NOC23 MA25. In this week, Professor Kumar covered concepts such as iterative methods for solving systems of linear equations as well as root finding methods. In iterative methods, we first taught us important concepts like norm of a matrix such as Frobenius norm, column row sum norm, and column sum norm. What is a diagonally dominant matrix? And then going on to touch upon the Jacobi method and Gauss-Seidel method as two types of iterative methods. We also touched upon convergence theorems, specifically how to figure out if your iterative method will converge to your final solution as the number of iterations keeps on increasing. Finally, we moved to root finding method, where we studied the bisection method, fixed point method, Newton-Raphson and secant method, also touching upon their orders of convergence and understanding when a particular method will give us a converging solution or not. With this all content in mind, as is the norm for every week, we have selected a few curated questions which will try to cover all of these concepts. We'll go through them one by one together. So, problem number one, it asks, consider the given system of linear equation and choose one from the given options. So we have been given a system of linear equations in three variables x, y, and z. We have three equations, and we are asked to state if if the system has a solution, and if it has a solution, whether it has a unique solution or infinitely many solutions. So I'll write down this system of equations in matrix form. So we have Ax equal to B, uh, where x underscore denotes the x vector given containing all the three variables x, y, and z. Vector B is the coefficient, gives us the coefficients on the right hand side of the equation, and matrix A is the coefficient matrix, which is 1, 1, 2, 2, 3, 1, minus 1, 2, 2. Now what I'll do is write the augmented matrix A augmented B, which is 1, 1, 2, 2, 3, 1, minus 1, 2, 2, along with the column 1, 2, minus 1. We'll be using Gauss elimination. So to determine if the system has solution or not, we could also have other methods such as checking the determinant of coefficient matrix, which essentially determines if the coefficient matrix is singular or not. In our case, we have to apply elementary row operations. So our first elementary row operation is R2 goes to R2 minus 2R1 and R3 goes to R3 plus R1. With this in mind, we essentially rewrite our coefficient augmented matrix as with these operations. So the row 1 is unchanged, as you can see. Right hand side will also be unchanged. Then for row 2, it is row 2 minus 2 row 1. So 2 minus 2, which is 0. 3 minus 2 will be 1. And 1 minus 4 will be minus 3. Similarly, 2 minus twice of 1 should give us 0 here. For the third row, it is row 3 plus row 1. So minus 1 plus 1 is 0. 2 plus 1 is 3. And 2 plus 1 is 3. And 2 plus 2 is 4. And again, the last two will sum up. So we have 1, 0, 0. Next row operation that we apply is R3 goes to R3 minus 3R2. So you can see that we have one pivot after the first row operation. We are trying to obtain the second and third pivot. Again, row 1 is unchanged. Row 2 is also unchanged. For row 3, what do we have? So 3, 0 is here. Then 3 minus 3 is 0. And 4 minus, and 4 minus 9 would be 13. So you have three non-zero pivots. This basically gives us solutions as 13z is 0 or z is 0, y minus 3z is 0, which gives y is equal to 0, and finally you have x plus y plus 2z equal to 1, which gives x equal to 1. So we can quickly substitute these here and we can see that this indeed gives us the solution. So from our augmented matrix, after applying elementary row operations, which is how we go about doing elimination method rather, what we obtain is three non-zero pivots for three equations, which essentially gives us that this system has a unique solution. Now we move to problem number 2. We want to consider the system of linear equation which has been given and then find the row sum norm of the corresponding coefficient matrix. If I write the coefficient matrix for this particular system, it turns out to be 1, 1, minus 1, 2, 3, 5, 5, minus 1, 2. Okay, so the row sum norm is defined as max over row I summation over j norm of aij. So if we take the first row, it's essentially norm of 1 plus absolute value of 1 plus absolute value of minus 1, which is 3. If we take the second row, we have modulo 2 plus, sorry, absolute value of 2 plus absolute value of 3 plus absolute value of 5, which turns out to be 10. And if we take the third row, we have absolute value of 5 plus absolute value of minus 1 plus absolute value of 2, which turns out to be 8. Now we want to take the max of this. So this turns out to be row sum norm for coefficient matrix A turns out to be 10, which is option C. Similarly, if in case we are interested in finding the column sum norm, it's nothing but max over j summation I norm of aij. And if we want to calculate the Frobenius norm, it would be summation I summation j sorry, I think I'm making a mistake here. Summation I summation j aij whole square and then taking the square root. These norms, if you may recall, these norms play an important role in figuring out convergence of any iterative method. The third problem, find the solution x of 1 after iteration of after one iteration of Gauss-Jacobi method for the following system of equation with the initial guess x of 0 is equal to 1, 1, 1. So we have been given of 0, which is nothing but x0, y0, z0 to be equal to 1, 1, 1. Now, if you recall the Gauss-Jacobi method, in Gauss-Jacobi, we can write the ith component after k plus 1th iteration to be 1 upon ai times bi minus summation aij xj of kth iteration where j should not be equal to I. So how does that look for our case? So you have x0, y0, z0 and after first iteration we'll have x1, y1, z1. So x1 is nothing but 1 upon a11 b1 minus, so a I is 1, so a12 y0 plus minus plus a13 z0, which if you substitute a11 is 1, b1 is also 1, a12 is a12 is 1 times y0 which is 1 plus a13 is also 1 times y0 which is 1, so you end up with 1 minus 2 which is minus 1. So if you want, we can solve it, but from the options, it's quite clear that it should be B. But I'll just solve it here. Y1 is nothing but 1 by 822 B2 minus 821 X0 plus 823 Z0, which in this case turns out to be A1 to A22 is minus 1, so minus 1 times 21 minus A21 is 3 into A21 is 3, x0 is 1, a23 is also 3, z0 is 1, so 3 into 1 which is 3 plus 3, so this should be minus 50. Similarly z1 is 1 by a33 b3 minus a31 x0 plus b31 y0. Here a31 is 2, x0 is 1, b31 is b31 is sorry a31 is 1, y0 is again 1, b3 is 9, a33 is 3. So this is 1/3 of 9 minus 2 plus 1 which is 3. So we should end up with 2. So after one iteration our uh, vector should look like minus 1 minus 52, so which is option B. Now we move on to problem number 4, which asks us to find the solution x of 1 after one iteration using Gauss-Seidel method. We are provided with an initial guess and we are given a system of equation. So for Gauss-Seidel method, if you remember, we take certain information of the updated guess. So if I want to write in formula terms, it would look like xi of k plus 1 is equal to 1 by aii pi minus summation j less than I aij xj of k plus 1. So this is the updated guess part minus summation j greater than I aij xj of kth iteration. For our case, this formula would look like x1 is equal to 1 by a11 b1 minus, so I is equal to 1, so j will always, so j can be either 2 or 3, so only this term will come. So you will have A12 Y0 plus A13 Z0, which in our case would look like A11 is 2, B1 is 16 minus A12 is 5 into 1 plus 1 into 1. So 16 minus 6, 10 by 2, which is 5. Updated guess for Y would be 1 by 8 to 2, B2 minus A21 X1 minus A23 Z0. So A22 is nothing but 1. So 1 by A22 will be 1. B2 is 11. A21 X1 is A21 X1 is 3 into 5 minus A23 is 9 into Z0. So Z0 is 1. So 11, 15 minus 4 minus 9, which is minus 13. So the final variable that we had was the second value of, sorry, the updated value of Z, which would be 1 by A33 times B3 minus A31 X1 plus A32 Y1, which in our case turns out to be 1 by 3 times 5 minus A31 is 1, X1 is 5 plus A32 is 2, Y1 is minus 13. So 5 and minus 5 should cancel out and we should get 26 by 3 as the updated value of Z. So our overall updated vector, solution vector should look like 5 minus 13 and 26 by 3. So that covers an example for Gauss-Seidel method. Next, we have a problem which tries to target convergence of iterative methods, rather asks about convergence of iterative methods. So we are given a system of linear equations and we are asked to determine if which of the following statements given below are true. So if you think about, if you go through the statements, they essentially say that Gauss-Seidel and Jacobi methods either converge for all cases or do not converge for any cases, or Gauss-Seidel converges but not Gauss-Jacobi, or the other way around. So we have to establish convergence of both Gauss-Seidel and Gauss-Jacobi method. So from convergence theorems, we have a few conditions which we can use. The most straightforward out of them is finding if the coefficient matrix for this given system of linear equations is strictly diagonally dominant or not. Yeah. Okay. So in this in this problem, we essentially want to find if this if if the iterative methods Gauss-Seidel and Gauss-Jacobi methods, whether they are convergent for any initial guess or not. For the same, we have a few conditions coming from convergence theorem. The most straightforward out of them is the condition which checks if the coefficient matrix for this particular system of linear equations is diagonally dominant or not. If it is diagonally dominant, then we know that both the iterative methods will converge for any guess and we don't have to do anything else. So we'll look at the coefficient matrix. It looks like 9, 1, 2, 2, 7, 1, 3, 4, 8. If you remember from the class, diagonally, the definition of a diagonally dominant matrix by rows is AII. Absolute value of AII should be greater or equal to summation of absolute values of Aij, where j is summed over 1 to n and j is not equal to I. So this is diagonally dominant by rows. And for convergence theorem, we need the strict inequality to be true. So we'll check for all the three rows. So for row 1, you essentially have left hand side is 9, right hand side is 2 plus 3, which is 5. So this holds strictly true. For row 2, you have left hand side to be 7, right hand side to be 1 plus 4, which is again 5. So again it holds true. And the third row you have left hand side to be 8, right hand side to be 2 plus 1 being 3. So for all three rows, we are able to show that the diagonal component AII is has much is strictly greater in magnitude than off diagonal components for that particular row, which essentially is the condition that our matrix A, coefficient matrix A, is strictly dominant, strictly diagonally dominant. And with this condition, we note that with this condition, we can say that both Gauss-Seidel and Gauss-Jacobi methods will converge for any guess, any initial guess. So that covers. Okay, if if this condition is not true, or on a if we cannot verify this, but if we have say an iterative iteration matrix xk plus 1 to be equal to g times xk plus h, if we have this iterator matrix, then we can also look at any norm of g. If it is strictly less than 1, then also the two methods converge. And the third condition would be if the spectral radius of the G matrix is less than 1. So spectral radius, to recap, is like for a given matrix G, we find out its eigenvalues, which would be say lambda 1, lambda 2, lambda 3. Then we look at the magnitude of those eigenvalues, mod lambda 1, mod lambda 2, and mod lambda 3, and we take the maximum of those values. So we would have spectral radius to be max of I modulo of lambda I such that lambda I is an eigenvalue of G. So this is your spectral radius. With this in mind, I hope this is clear. If not, you can ask any doubts now. Otherwise, I'll move to the next problem. So problem number 6. This deals with root finding methods. So the first set of problems that we covered so far basically covered convergence of iterative methods, an example of Gauss-Seidel method, an example of Gauss-Jacobi method, then norms of matrix, different norms, and trying to solve a linear equation from using direct method. So that covers first half of the problems that I had. For the second half, we'll be looking into the different root finding methods which were covered. Specifically, these include bisection, fixed point, Newton-Raphson, and secant methods. So the first problem deals with bisection method. We are given a function f of x equal to x cube minus 2x minus 5, and we want to find its root within the within the interval 2 to 3. We want to get the approximate value of 2 of the root after 2 iterations. So I'll write a, b, and x is equal to m is equal to a plus b by 2. So we need one more column. We need a few more columns here. So I think I'll just write in tabular format. A is my left bound, f of a. B is my right bound, f of b. And my m is my midpoint, and I want f of m. So for the zero, and here I have an iteration column. For the zeroth iteration, we are given a to be 2. So f of a would be 2 cube, which is 8, minus 2 into 2, which is 4. So 8 minus 4, which is 4, minus 5. So f of a is minus 1, and b is 3. So 3 cube, 27, minus 2 into 3, which is 6. So 27 minus 6 will be 21, minus 5, which is 16. My midpoint is m is equal to a plus b by 2, which is 2.5. Now we can note that before we move further, we can note a couple of things. Firstly, the function f of x and the bounds that were given a and b. Here we have the condition f of a into f of b is less than 0, and f of x is continuous in the interval a to b. If these two conditions are satisfied, then the bisection method is globally convergent, which essentially in our case means that there exists some alpha belonging to the interval a comma b such that f of alpha indeed vanishes to f of alpha goes to 0, or alpha is indeed a root of f of x. So with this in mind, we have our initial bounds as 2 and 3 and the midpoint as 2.5. So my f of m is equal to 2.5 cube minus 2 into 2.5, which is 5, minus 5. So which is 6.25 into 6.25 into 2 point. So my f of m is f of 2.5 for this particular case, which is 2.5 cube, which is 15.625 minus 2 into 2.5, which is 5, minus 5. So this is 5.625. Now to find the new bounds for iteration, we look at f of a into f of m if it's less than 0. In our case, f of a into f of m is less than 0, which means a and m become the new bounds. So our new bounds are 2 and 2.5. Again, this is minus 1, this is 5.625, and this is 2.25. So my f of so my function value would turn out to be 11.2.25 cube minus 2 into 2.25, which is 4.5, minus 5, which turns out to be 1.890625. Yeah, yeah. So, so we end up with our new bounds are essentially f of a. Again, f of a and m become our new bounds. So for the second iteration, our bounds are 2, 2.25, minus 1, 1.89, and so on. And my midpoint will be 2.125. So after two iterations, our best our best case value should would be the midpoint of these two iterations, midpoint of the bound of after second iteration, which is essentially 2.125. So yeah, I think I made a mistake with this option. This essentially should be 2.125. So in bisection method, in bisection method, we always have bound. We always have like the two ends of the bound, but we when obtaining the best estimate after some number of iterations, we need to give a single value, so we can, like, the norm is normally to just give the midpoint of the bracket after nth iterations. Now we move to problem number 7, where we are asked to find approximate value of root of this equation using fixed point iteration, and we are given the initial guess to be 1.5, again after two iteration. So in this case, we have f of x, we want f of x equal to 0, so 2x cube minus 5, which gives us x is equal to 2x cube minus 5, or um, x is equal to x plus 5 by 2 cube root. So which of these, I'll write first one as g1 of x and second one as g2 of x. Which of these should we use? So for fixed point iteration, we know that if suppose if we have g of x for all x belonging to a to b, which contains root, then we require modulo of g of x to be strictly less than 1. Then if modulo of g of x is less than 1, it means that our solution will converge to fixed point. Okay, with that in mind, suppose we take g1, derivative of g1, that is essentially, so first we need two bounds. To begin with the two bounds, suppose I take a is equal to 1 and b is equal to 2, then my f of a is 2 minus 1 minus 5, which is minus 4, and my f of b is 16 minus 2 minus 5, which is 9. So f of a into f of b is less than 0 and f is continuous or a to b. So which gives me these two bounds 1 and 2 as my bound containing the solution. And if I now take the first derivative of g1 and g2, it would look like 6x square, and you can see that modulo of this would always be greater or equal to 1 for all x belonging to a and b. Similarly, if I choose my second function, it will be 1 by 3 g2 1 by 3 into x plus 5 by 2 raised to 2 by 3 into 1 by 2, so which is essentially 1 by 6. Now you can see that this modulo will be strictly less than 1 for all x belonging to a comma b. So g2 becomes our choice of function for a fixed point method, which basically gives us, so we are given, so we now have x1 is equal to g2 of x0, which is x0 plus 5 by 2 cube root, which is so 6.5 by 2, which is 3.25 cube root. If we check, turns out to be 1.0833. If I take x2, which will be g2 of x1, which turns out to be 1.0833 plus 5, which is 6.0833 by 2, so that would be cube root of 3.0416 bar, which is 1.478. So the closest is 1.479. With this fixed point iteration clear and the condition of the same also clear, norm of g dash, we now move to problem number 8, which is an example of Newton-Raphson method. So we are given f of x is equal to x cube minus 7x squared plus 8x minus 3, and we are asked to find approximate value of root using Newton-Raphson method. So Newton-Raphson method generally converges faster. It has second order convergence, but its limitation is that you usually need your guess value closer to your root value. So for Newton-Raphson method, the update rule is given as xk plus 1 is xk minus f of xk upon f dash of xk. In our case, f of xk, f dash of x would be equal to 3x square minus 14x plus 8. So if I want to write x minus f of x upon f dash of x, it will be nothing but x into f dash of x minus f of x upon f dash of x, which is so 3x cube minus x cube, which is 2x cube. Then on the x square term, we have minus 14x square minus 7x square, so which is minus 21x square. Then you have plus 8x minus 8x, which is so x term would be cancelled out, and then 0 minus 3, so plus 3 upon 3x square minus 14x plus 8. So this becomes our polynomial, so I'll write this as g of x. So my x1 is nothing but g of x0, which if we substitute the values, it turns out to be 2 into 2 cube, so 2 into 8, which is 16, minus 21 into 4, which will be 84, plus 3 upon 3 into x, so 3 into 4, which is 12, minus 28, plus 8. So if you sum those up, 16 plus 16 minus 84 plus 3 is nothing but minus 65 upon minus 8. Well, 820 minus 8, which turns out to be 65 by 8, which is 8.125. So to find the value of x after second iteration, we just have to plug the x1 that we have obtained, and after putting it, in our case, we find that the value comes out to be roughly equal to 5.72, 5.719, which is option B. Now we move to problem number 9. In problem number 9, we are asked to find the approximate value of root. after first iteration using second method. So in second method, we approximate the first derivative of f of x by using a finite difference. So essentially, xk plus 1, xk plus 1 is equal to xk minus f of xk upon approximate value of the derivative, which is f of xk minus f of xk minus 1 upon xk minus 1. Now, if you were to simplify this essentially turns out to be xk minus 1 into f of xk minus xk into f of xk minus 1 upon xk minus upon f of xk minus f of xk minus 1. So for our case, this is we have f x0 is equal to 1, f0 is f of x0, which is 2 into 1 cube minus, so 2 minus 2 minus 5, and x1 is 2, so f1 is f of x1, which is 16 minus 4 minus 5, so this turns out to be 7. Therefore, our x2 should be equal to 1 into 7 minus 2 into minus 5 upon 7 minus 5. So 7 plus 10 is 17 by 12, which is option D. And finally, for the final problem, again we have second method. Again, we'll do the same thing. So we want to find the approximate value of root after first iteration using second method for this particular polynomial. So we are given x0 to be 1. Therefore, my f0, which is f of x0, would be nothing but 1 minus 1 minus 1, which is minus 1. My x1 is 2. Therefore, my f1 is f of x1, which turns out to be 2 cube is 8 minus 2 minus 1, which is 5. Therefore, my updated approximate value of the root is x2 is equal to x0 f1 minus x1 f0 upon f1 minus f0, which is 1 into 5 minus 2 into minus 1 upon 5 minus 1. So this is 5 plus 2, 7 by 6, which is option number B. Option C, sorry. So these are all the problems that I had for this week. So we have covered we have covered examples for all the four root finding methods, which are bisection, fixed point, Newton-Raphson, and second method. We also looked at problem for one single problem for direct method while solving a linear system. What are different matrix norms? What's a diagonally dominant matrix? Different types of iterative methods, specifically Gauss-Jacobi and Gauss-Seidel. Then how do we figure out if the methods are converging or not? All these concepts have been covered in this week's lectures as well as through these sets of problems. If there are any doubts for this week, now is the time to ask. You could also post them on the forum. If I'm guessing there are no more doubts right now. So anyways, thank you for attending and joining for this week's live interaction session. We'll be again meeting next week where we'll cover the concepts taught in week 6 of the lecture. Thank you for your time and attention.